So by this stage in the course, we hope you know the syntax of a programming language. What is a program? What is a command? What is an expression? Etc. etc. And how you, and parsing and lexing, which turn strings or tokens into the syntax trees, which the computer then can go and manipulate. But what you don't know is, what does a program do? So you know what it looks like, you know what it is. It's a definition, it's an integer expression, it's a whatever. You know what they are, but you don't know what they do. And that's this question about why is new being used for substitution. It's because we haven't told you yet what new does. We've just said that new is a keyword, followed by a variable, followed by a colon, followed by an equals, followed by an integer expression, followed by in, followed by an integer expression. That's all we've told you about new. And obviously, it doesn't tell you very much. So that's what we're going on to do now. What does a program do? So this is what's called big step semantics. Sorry. This is called big step semantics. It's semantics. Semantics is the word for meaning. What does a program mean? You know, when you write a program down, you press return, you get its meaning. So that's why it's semantics. And it's big step because I'm going to tell you what a program does in one go. There's a variant of this, which we'll do later, where we tell you little chunks of how you sort of move from the program in step-by-step ways to the answer. That's small step semantics, because you take little small steps. Here we're going from there to there in one big step. So that's what we're doing in this lecture. Big step semantics for the language IMP. Right, put that there. Now, so I'm not sure about you. So this is the first time I've taught this course. Actually, it's the first time anyone's taught this course because it's a new course. It was done previously in ways which we think are horrendous. But don't tell Richard. I mean, I guess you can if you want. He'll just say that what we're doing is horrendous, but never mind. Anyway, so when I came to it, I realised this is quite an exciting course to do. I think, you know, in your course, in your journey from when you started to when you end, there are moments where you start doing really significant stuff. This is one of those moments. So it's cool stuff. It's not writing programs. It's writing programs that implement other programs. I mean, that's really cool. But as a result, there's a lot of complexity involved in it. You know, if you looked at the grammar for IMP, it's quite big. You know, you've got blocks, you've got commands, you've got integer expressions, you've got Boolean expressions, lots and lots and lots of stuff. That's because programming languages are big. So in order to demonstrate what I'm talking about with big step semantics, I'm going to first of all do a little cut down fragment, and then I'll tell you about how we do it for real. So let's consider a simple fragment. So let's have an integer expression. And these are going to be much simpler than the integer expressions that you've previously got. They're going to be either numbers, or they're going to be an integer expression followed by an integer operator followed by an integer expression. And what's an integer operator? It's just going to be plus or minus. Okay, so that's a small, tiny part of what you had before, of what's in the IMP language. It's very, very simple. There are no commands, there are no assignments, there's no do, there's no that's it. Very simple. Right, so how do we say what this program does? Well, we have to say, so to say what the program does, well, it's going to give you some kind of value. What's the output? So you've got to first of all say what the output is. 2, then for every one of these production rules, you've got to say, how do you turn a program used with that production rule into a value? So, how to turn a program defined by each production rule into a value. So that means, if we define our program with this, how do you turn that into a value? And if you define our program with this, how do you turn that into a value? First of all, what is a value? What is the output value? Now this is very, very simple. It's chosen to be very simple, so you get the flavour of what's going on. And here the values are obvious. Values are just integers. If you just look at it, it's clear that, if you type something like this into the terminal, press return, you ought to get an integer back. So that's what the values are. And you'll see later on, we've got to choose what values are. And then we have to say, how do we turn a program defined by each of these production rules into a value? Well, so what we're going to do is we're going to have what are called judgments. And we're going to write them of the form. So they're going to look like this. E, that's an expression, that's an equal sign turned on its head, and then a sort of arrow at the bottom. So it's a downwards arrow, n. So this says, this program E will evaluate to the number n, the value n. So that's what we're going to do. We're going to be writing these judgments. And all throughout this lecture and the next lecture and the second homework, you're going to have practice in writing all sorts of different judgment forms for all sorts of programming languages. So this means the program E evaluates to the value n. And notice these are different things. I mean, some programs are numbers already. That's quite cool. But of course, there are many, many more things over here. But they all have to come down to an integer at the end. All right. So how do we do that? Well, we just write a series of different rules for showing that. It's very simple. So here's our rules. Here's our rules. So there are two production rules I'm interested in from the previous grammar. One gave me numbers, one gave me integer operators. So let's see. So we write them like this. So again, I'm going through it slowly so you can get the form of it. So each rule has a horizontal line. And below is the output. And above is the kind of pre-processing that we need to do. So for example, let's do the rule for addition. So I'm interested in, one of the production rules says an integer expression is an integer expression followed by a plus, followed by an integer expression. So I need to tell you, what does that reduce to? What does that evaluate to? So on the bottom, below the horizontal line, I'm going to write the expression I want to evaluate. So how do I do this? Well, do you remember in the first lecture we said, you process the subtrees and then you do the overall answer. So the natural first thing to do is to ask yourself, what does E1 reduce to, evaluate to? And let's say maybe it reduces to some number N1. And then maybe E2 reduces to some number N2. So we process the subtrees, we work on the fragments of the program, the components of the program, and then we can work out what the overall answer is. So, well, if E1 evaluates to N1 and E2 evaluates to N2, then overall E1 plus E2 should evaluate to N1 plus N2. It's pretty obvious. I'm sure you could have guessed that. I guess I should make the point that these are different pluses. Is that obvious? This is the plus that works on integers. If that's 7 and that's 12, this is 19. It's not 7 plus 12, it's 19. It's plus on integers. I mean, we know these are integers, so we can do the plus. But this plus is just the plus from the production rule. It's syntax. It's the plus symbol you type on your keyboard. It doesn't actually do any addition, it's just the plus symbol. And this can be complicated, and this can be complicated, so this is just a symbol. So that's a syntactic plus. A syntactic plus which works on expressions, and a plus that works on integers. Okay, so in general, as a programming language designer, once you fix the syntax of the language, you're then going to have to start saying how each different syntactic category or each different production rule gives you a value. When you've done that, you've said enough for the computer to implement that and actually reduce any program to its value. And we do this by just kind of working back up the tree. So we're going to do an example. How many of you have seen natural deduction style trees before? Ah, I thought not. So we're going to do this slowly. So here's a big expression. So I want to work out what 5 plus 4 minus 3 plus 6 plus 4 evaluates 2. Okay? Oh, yes, you can still see it. So we're going to do this example. And in the next homework, there'll probably be some simple examples like this. This is the basic stuff to make sure you get your first mark. So, what are we going to do? Well, you know in your head what you would do. You'd say, oh, well, 5 plus 4, that's 9. Then I take off 3, that's 6. I've got 6 there. And then I've got 6 plus 4, that's 10. So then I've got 6 plus 10, it's 16. And all we're doing is mimicking that process. You know the answer. All we're doing is taking your knowledge and writing it down formally in a language that a computer can understand. So you see, with this rule, formally it says, I've got a plus formula down there. So therefore I can use this rule. And this rule says, first of all, work out what the first expression reduces to, then work out what the second expression reduces to, and then combine them for the answer. So I can use this rule. So there's no magical thinking required here, there's no intuition, there's no creativity. This is just an algorithm. So you just follow the rules. So it's very easy. The hard stuff is creativity. So, okay, the rule says, well, first of all, what is 5 plus 4 minus 3? What does that evaluate to? And then what does 6 plus 4 evaluate to? So this is what you should be writing down. I mean, not particularly. If you want to write it down now, that's fine. But I mean, when you do your coursework, this is what an answer looks like. Okay, so that's what the previous rule said. So what does 5 plus 4 minus 3 work out? So in your head, you say, oh, well, that's 6. But the computer's going to have to say, what sort of formula is this? Oh, it's not a plus formula. It's a minus formula. This is defined by the production rule for minuses, not pluses. I hope that's obvious. There is a plus inside here, but the production rule we used is minus. That is the top level. If that's not clear, then you should either ask your friends, or ask me, or ask Connor, or ask Stuart. It's an important thing you know that if we give you a complex expression, what's the actual production rule used? Because you need to know the production rule so you can figure out which of these evaluation rules is needed. So anyway, here we need a production rule for minus. I didn't actually write it. I only wrote the production rule, the evaluation rule for plus. So we need the evaluation rule for minus. So what does E1 minus E2 evaluate to? Okay, so it's always good if we have some interactivity rather than you just listening to me, because you'll either get bored or you'll fall asleep, or both, none of which are productive. So I'm going to say, what should I write here? I mean, you've seen the evaluation rule for plus. This is going to be fairly similar. So it's going to look fairly much like that. So what should I write here? What do I need to do to evaluate E1 minus E2? What do you think? If I said, how would you go about evaluating this? Yeah, I would think about, well, the first thing I need to do is work out what E1 is. Okay, so let's evaluate, so let's say we want to evaluate E1. Okay? Very good. What do you think we should write next? Yeah, so we say, well, let's evaluate E1, and we have to say what the answer is, because we're going to use the answer. So maybe if E1 evaluates to N1. That's a good start. What do you think we should do next?
E2.
Yeah. So of course now we need to figure out what E2 is. So let's try and evaluate E2. Nice band, by the way. Is that your favourite album? Right, where have we got to? Okay, so we worked out that E1 evaluates to N1, E2 evaluates to N2. Okay.
So would it all be N1 minus N2?
Yeah. As I say, these are very simple formula. You know, they're so simple they might seem trivial, but believe me, when it comes to doing mu later on, it gets quite, you know, you have to think very, you have to get into a Zen state to kind of see what's going on. But these are very simple, they give you the idea. As I say, you always evaluate the sub-expressions, see what they give you, and then figure out how you combine the results to the overall answer. So now that we have the evaluation rule for subtraction productions, we can carry on with our overall problem of figuring out what the answer to this is. Okay, so your turn next then. So what should I write next?
What does 5 plus 4 evaluate to?
3, yes. So what should I write? What would you write? What's the next thing you'd write? When I wrote this part down, whoops.
We need to figure out what the first part, which is 5 plus 4 evaluates
Exactly.
to, and the second part,
Exactly.
minus 2, whatever.
But there's even something smaller, which is so small you skipped over it. When I first of all wanted to know what this thing evaluated to, I built up my syntax, my natural deduction tree by writing a line, because I'm using one of these rules which have lines in the middle. So what I should do is say, okay, let's have a line here. And then what you've done is you've given me the answer to the next bit, which is good, because you're getting ahead. That makes your job quite easy if you're paying attention. So what's the next thing I should write?
5 plus 4.
Yeah, so I look at this, I say, oh, well, how am I going to evaluate this minus formula? Well, I've got a rule. It says, first of all, evaluate the first component. So I'll write 5 plus 4 evaluates to, and then it says evaluate the second component. Okay, your turn next. What shall I do?
5 plus 4 evaluates to 9.
Right. Okay. Yes, you're right. So what you're doing is you know the answer, so you're telling me the answer. And with these simple expressions, that's fine. I mean, we could have just stuck, what was it, 19, 20 or something? We could have just written the answer there. So we have to sort of get out of the knowledge we have where we're acting like the computer and just do what the computer would do. The computer will work much, much more slowly because that's where it is. So the only rules, what we haven't got, oh, hold on a second. So we've got 5 plus 4. So we have to use one of these rules. We can't do anything else. That's where there's no creativity. You must use a rule. So, can you use the plus rule to evaluate 5 plus 4?
Yeah.
Yes. It's very easy when you get the hang of it. You know, you're a bit nervous, but no, yes, that's right. So we just use the plus rule. So what that say?
5 evaluates to 5.
Okay, we'll do that in a minute. So the plus rule says, first of all, evaluate the first expression and then the second expression. Okay, so we can have that much. Okay. Right. 5 evaluates 2. Okay. Which rule can we use out of these two? It's next.
The top one.
No, because this is not this 5. That's not an addition expression, is it? It's not something plus something. Sorry, I'm being a bit naughty. That's right. I gave you rules for plus expressions. There we are. Oh, no. Where have I gone? Yes. I gave you rules for pluses and minuses, but I didn't give you the rule for numbers, how to evaluate numbers. It is trivial, and I should not wave this pen around so close, but I still do need to give you it. So, here's the rule. It just says, what does a number evaluate to? Guess what? It evaluates to itself. And you don't need to do any preparatory work, because you know the answer. So now, go to the next. What can I write?
5 evaluates to 9.
Yep. Well, I'll only ask you a little bit. I want to get around to those hiding at the back. What do you think 4 evaluates to?
4 evaluates to 4.
Right. Okay. So now let's think about this. Now we can do this part. To use this to evaluate 5 plus 4, we had to evaluate 5, we had to evaluate 4, and then use the plus rule. We've done that part, so what can I write here? 9. Exactly. And so again here we'll get 3. So then we'll use the subtraction rule, which will say 9 minus 3, which is 6. And again, I'll finish it off now. So 6 evaluates to 6, 4 evaluates to 4. And then the plus rule will say 6 plus 4 evaluates to, well, this 6 plus 4, which is 10. And then this plus rule will say that this thing evaluates to 6 plus 10, which is 16. So that's how big step semantics works. Any program here that you want to evaluate, it has a particular production rule. That's the point of the grammars, that's the point of the syntax tree, to tell you what the production rule is. And then all you do is you look at your list of evaluation rules, and there should be a rule for that production rule, and then you just apply it. And you might have to recursively, do a few more steps, and your tree will grow upwards. And then finally, when you start getting the answers, it's all cascade down to the bottom again. Okay, any questions on that? So that's an example. Good. How much time have we spent then? Half an hour, right. Okay, so that's a very simple language. Trivial, very simple. But you get the hang of it. All we're going to do is that kind of thing, but for more complicated things, with commands and with mews and do's and returns and ifs and etc. And essentially, for each of those things I've just mentioned, we're going to have an evaluation rule. And then each of those evaluation rules can be used to evaluate any program. So conceptually, what we've just done, this is all there is to it, conceptually. Technically, these rules will get longer and more complicated, it'll be intricate and whatever. So you'll have to manage the details. But conceptually, this is all that's going on in this lecture. If you understand what we've just done, you've understood conceptually this lecture. Right. So, what's more complex in the IMP grammar that wasn't in what I just wrote down? Well, there's a whole load of things about commands and assignments and, for example, x equals 7, and new x equals 5 in x in whatever. So it's called, the IMP grammar manipulates memories. They've got variables. And when you've got variables, you have to deal with memories. You can't evaluate x plus 7 unless you know what x is. So things are going to get more complex now because our judgment forms will get more complex. We'll need to know about the memory. So what's going on in IMP? Well, we have more production rules. Okay, well that's fine. You've seen 3 production rules. If IMP has 17 production rules, well, it's a bit long, but fair enough. Nothing much more difficult will happen. But also, we need to deal with memory. And 3, I'll come to this later, we need to deal with scope. Okay, so those are the 3 sort of extensions to what we've just done that we need to tackle in order to deal with the language IMP. So I'm going to talk about 2 next. So let's say if we consider do x equals x plus 1, return x. So if I say evaluate this program, the first thing you say is, well, what's x? So that's my point. We're going to have to generalize everything we do to have memories involved. So our judgment form is going to get slightly more complex. Oops. Ah! Right. So it's like what we had before. We're still saying this expression will reduce to this value n here. That bit's not changed. But we're also saying, actually, this expression will only reduce to a value in a particular memory. So in fact, what we're reducing is no longer programs. We're saying this program in this memory will reduce to. And then, what does it reduce to? Well, we certainly get a number, but the memory will change. So you see in this example here, yeah, we'll get a number. So if the memory says x is 7, first we'll make x 8, then we'll return 8. But also, the memory has changed. X will no longer be 7. So we get a new memory. And we'll have to track how the memories change. If we're doing x equals x plus 1, x equals x plus 2, then as x changes, we need to track that. So that's why we need to record the new memory. So this roughly says expression E in memory sigma value x2 integer in memory, oh no, sigma prime. So that's what this judgment form can be read as. This expression E, in memory sigma, evaluates to the integer n in the memory sigma prime. So just generalize the judgment form to stick memories in them. Okay. So that's one thing you need to do. Right. But IMP also has more than just integer expressions. It's got commands, it's got blocks, it's got Boolean expressions. And they all have production rules, and we need to evaluate all of those. So for example, with that do formula, that's an integer expression, but first of all, to evaluate the whole do integer expression, guess what? The first thing you do is evaluate the command x equals x plus 1. So you need a judgment form for evaluating commands. We need something to evaluate commands. So what does that look like? Well, obviously it'll have to start with a memory. So we'll have in a memory sigma, we'll evaluate a command. That'll evaluate to, well, you'll change the memory, and you think, oh well, and what do I get? And now this is part of the programming language design. So what should we get when we evaluate a command? I mean, if I start with a memory, x is 7, and I do x equals x plus 1, I'll get the memory x equals 8. Do I get anything else? If you think about it, you actually don't. Commands are different from expressions. Integer expressions give you an integer. Commands don't. They just transform the memory. So in fact, our judgment form for evaluating commands is just that. We don't get anything else. Okay, but there's other things in the grammar, wasn't there? There's Boolean expressions. So this is commands. This is Boolean expressions. So, if in a memory we evaluate a Boolean expression, what are we going to get? We'll get a new memory because, again, these Boolean expressions, they can contain expressions, and it could be like x plus 2 is bigger than 7. That's a Boolean expression, okay? So it has an x in, it has integer expressions in, so we get a new memory possibly. That can change. If you look at the grammar for Boolean expressions, you realize they can change the memory. Eventually you can find an assignment in the middle of there. And then at the end of it, we should get true or false. So we're using B for bit. So the values for Boolean expressions are bits. So we'll get a true or a false. And finally, if I'm not mistaken, there's blocks. Remember, a block is just a list of commands. It's like, x equals x plus 1, y equals x plus 2. That's 2 commands, it's a block. So we need judgment forms for blocks. Okay? Well, blocks is just a list of commands, so not surprisingly, it'll be something like sigma in some memory. If you have a list of commands, then that will reduce to a new memory. All we'll do is we'll take the first command, run that using the judgment for commands, then run the next one, run the next one, run the next one, and we'll end up with another memory. That's a C, by the way. And I've written CS because a block is a list of commands, many commands, so it's like pluralized. It's pluralized. But it's just a variable. But it's a convention about naming variables. Okay, so I've told you, reminded you, or pointed out to you, that we needed to generalize the judgment forms to have memories. And then also, because the grammar has commands and Boolean expressions and blocks, we also need to have rules for judgment forms for evaluating blocks and Boolean expressions. Now notice I've not actually told you how to, how to actually evaluate any of the particular Boolean expressions. I've just said what they will look like. So you still have to do all the hard work. But we're starting. Right. Let's see. Where are we now? A few minutes. Okay. So let's carry on then. Right. So now we have judgment forms. We can evaluate all the instruction rules. So let's see. In the grammar integer expressions we have, where's it gone? We have variables, we have values, we have additions, we have subtractions, we have new, and we have do. So for integer expressions, there are values, variables, plus, minus, new, and do. 6. So we need 6 rules, 1 for each of them. Just like the previous language had plus, minus, and numbers, so we had 3 rules. Integer expressions have 6 production rules, so we'll get 6 evaluation rules. Everyone with me? Who's not with me?
What's that word next to judgment?
Oh, forms. I just didn't want to say judgments because I'm using judgments for the actual things to do with pluses and things to do with minuses and numbers and do's and whatever. So, judgment forms. Everyone with me? Any questions? Remember, I might ask you a question later, so if you're not with me, best ask now. Cool? It's amazing getting into this stuff. My sneezes have gone. What that means. Right. Okay. Let's get on with it. So now I think I've told you everything you need to know to get on and do it yourself. Happy? You're happy. You're happy. You two are happy, but then you've answered questions already. Right, let's switch to blue. The meaning of blue. Okay, so I'll start you off. So remember, what we're trying to do is the equivalent of the rule for plus, which says evaluate E1, evaluate E2, combine the results. So let's do C. Let's do do. Okay, so I need to write a rule which will allow me to evaluate do expressions. And remember, the grammar for do expressions is do, a command, return, expression. And of course, like I've just said, actually to do an evaluation of a command, of an integer expression, we have a memory that goes along with it, which will change. So I'm expecting over here, the judgment form says I'm expecting new memory, a line, and then an integer. And that's because the judgment form for integer expressions told me so. Okay, where do we get to? I can't remember. How about you? What should we do to this do? Well, remember, when I said it was E1 plus E2, we worked on the fragments, the components, the bits of E1 plus E2. So what are the bits inside this do command?
C.
Yeah. First of all, we have to execute the command C. So we better try and evaluate that. That's a good start. So I'll write C down for you here. Okay? Your turn.
We've got E as well to return.
Yeah, there's an E here. So we better, at some point, we'll need to evaluate that. So let's put that here. Okay? So, I mean, different people try to get interaction in their class in different ways. I try and go through everyone. Because otherwise, I either get silence, or I get the smart aleck saying, pick me, pick me, pick me. You know? What I need to do is, especially those who are a bit unsure, I'm not saying you were unsure, but in case you were, I can just prompt you a little bit. And as usual, it doesn't take much prompting, you sort of get the ideas. So that's how I do my interaction in my classes. So that's C and C. So, obviously, in order to evaluate this do expression in this memory, we're going to have to do something to C and do something to E. So we've written C here and we've written E here. Okay, and you said E, so it's your turn next. And all you need to do is say a little bit. I don't want the full answer.
C and E will need to evaluate to something.
Yeah, so of course we need to evaluate C, so let's put our little evaluation symbols down. Okay. Can you think of what else we can do? Your turn. So, if I'm evaluating C, what does the judgment form for evaluating commands look like? I had it here a moment ago. There we are. I've already said that whenever I'm evaluating a command, they must look like this. This is why I said it's a judgment form. It tells you the shape, the form of it. This says I can't just evaluate a command. I need a vertical line before, I need the memory that command must be evaluated in. And as the result of evaluating it, I get a memory. So that's why these things are important, because they tell you the answer that you can use now. So, you've told me, or someone else has told me, I should be evaluating a command. What's the judgment form for commands? What else do I need to put there in order to evaluate my command?
The memory and the vertical line.
Yeah. Okay, so we need a vertical line and we need a memory. That's what the command form for evaluating command said. But which memory? Your turn.
The one beneath it on the first line?
Yeah, sigma. So to evaluate do C return E in the memory sigma, the first thing I should do is evaluate C, guess what, in the memory sigma. So you might have thought, I'll just evaluate C. But actually, oh, hold on a second. I'm changing the memory, so I'm always going to have a memory around. Which memory? Well, I'm starting the process, so it's the memory I start in. Okay, very good. Your turn next. You can't say you're surprised. But actually, those are the next line. You can imagine what bit you might have to do. Prepare. Okay, so the judgment form for evaluating commands says, give me a memory, separate it with a vertical line, give me the command you want, then write the evaluate symbol, and then what do I get?
An altered memory.
An altered memory. So let's call it sigma, because we're using sigmas for memories, but let's put a prime there to suggest it's been altered. So this says, let's first of all evaluate command C in the memory sigma, and let's say we get the memory sigma prime as a result. Previously, the additional ones it said n. Let's say we got the result n. Okay, but here it's a memory that we're getting. Okay, your turn.
I'm not sure what they just found the E at this point.
Right, so let's have a look. So now we're learning about E. Let's have a look at our judgment forms for expressions. So in the first example I did, it was just an expression evaluate to a number. But then I said, because we're going to have memories around, this is the judgment form. Whenever you want to evaluate an integer expression, you need to give it a memory, and then what you get is not just the integer you get, but the new memory. Okay? So, which piece of paper am I on now? This one. Okay, so, I'm working in this area. What else do I need to do? Can you see what we did here? We had to evaluate a command, so we did some things.
Yep.
We got what? You can't say yup.
I don't know what the next step.
Okay, how about a vertical line? So, the judgment form for expressions, I can do it this way, brilliant. Says, if you want to evaluate an expression, you must have a vertical line before it. It's like a syntax. You know, everything we do as people, we use language for. Language has syntax. So it's not just the syntax of your programming language. The syntax of the judgment forms come with the syntax. And it says, you must have a vertical line, and then you must have a memory, and you must have this symbol, and then you must have a memory, and then you must have, there's no creativity, there's no imagination. I mean, I'm not really into doing what I'm told, but here, because it's an algorithm, you just do what you're told, which is nice, because there's no creativity. So, I need to have a vertical line. The judgment form for integer expression said write a vertical line. Okay, what comes next?
The memory.
Yeah, so now I have to have a memory. That's what the judgment form says. But which memory? Your turn.
It's just the original memory.
The original memory? Are you sure? So if I say do x equals x plus 1, return x. So the x equals x plus 1 will increase x by 1. And you want to use the original memory?
So it's the altered memory.
The altered memory. It is the altered memory. So now we're getting into some more complications. When we did the numbers, it's trivial. But now it's here. You see, it's at this point that we're saying what programs mean. We're saying, what does do C return E mean? And we're saying that it means execute this command, and that will change the memory, and evaluate this expression in the changed memory. This is where we say that formally. Okay, so what is the actual change in memory? Your turn? Yeah?
Sigma prime.
Yeah. Sigma prime was the memory that we got when we evaluated C in the original memory. Okay, so that's good. So we evaluate C, we get a new memory, and we use the new memory to evaluate E. Your turn? What else happens?
The evaluated one be sigma prime than a number.
Okay, is that what you meant?
Yeah.
Okay, close, but that's actually not quite true. What do you think?
I think that it should be another altered
Yeah,
signal.
because when you change this E, when you evaluate this E, the memory could change again. See, by writing sigma prime, you said that you must get the same memory you start with when you're doing E. Actually, there's no reason you should. So it could be just a completely different one. Okay, so now we've done the pre-processing. We've thought about E, we've thought about C, we've evaluated them. How do we put the results to get the overall result of evaluating do C, return E in the memory sigma?
So should we repeat the last expression? So we would show the twice altered memory. And
Yes.
the integer.
So overall, what's the new memory when you've finished evaluating all of this? Sigma double prime. When you've finished doing C, and then you've done E, you've done all the memory changes you're going to get, and you're going to end up with sigma double prime. And then, yep, the value you get is N. That's the value of E in the right memory. Only 16 more rules to go. But you see what I mean? I hope you're getting a flavour. It's all mechanical. Once you know what your program is doing, then it's just writing it down. Okay, it's writing it down not in the English language. It would have been nicer if I could have said, to evaluate do C, return E in the memory sigma, first of all, evaluate C in the memory sigma to get to memory sigma prime, and then evaluate. I could have written that down in the English language, or any natural language, but those languages aren't precise. People might misinterpret them. We have to use an absolutely formal, precise language to be sure that we've written something down that's unambiguous. And I'm afraid that means mathematical, logical symbols like this. So, it takes a little while getting used to, but if you remember what you're doing, then then we can get to here. All right, so thanks a lot. And remember to put your 1-minute papers inside here.